On this episode of Pipeline Things 666, eschatology and the end of all things to come, as we talk about pipeline dents. If you don't know what TMS means, then you're not in the know, and you're going to need to listen to this episode. Thanks for joining us. All right, welcome to this episode of Pipeline Things. When we are continuing our conversation, I'm enjoying this series that we're heading into because I love talking about the stories that define us as an industry. And I like getting into some of these questions where people are always like, where did that come from? And sometimes people kind of halfway know. Sometimes there's the rumor mill out there, but we don't always know.
This is a missed opportunity, right? I'm going to jump in here. Like, if we are careful with how we do this podcast, we could just make stuff up. Like Sarah's told us, we're starting to have enough expert evidence on Google's SEO that we could just like redefine what history was.
When do you think the first time we'll get referenced in a publication will be?
Like according to Pipeline Things, June 5th of 2026.
That'll be funny. But I can't self-reference, that's for sure. We can't reference. Oh, that's too
guaranteed.
much.
AI is already paying attention.
Well, did our guest just jump in?
Did he just jump into our podcast?
Did you already let him in?
I did. AI is already paying attention. They're going to remember this.
Wow, that is also a first. I want you to know.
We always introduce the guest, and
the guest just
surprise.
It's like self-excavating pipe. We have a self-introducing guest. So you know what I was thinking about today's topic, Mike. Now you're a part of the segue.
Now you're
Welcome. This is the first. I have to fly a lot. Like people always ask me how much I travel. Probably like what, Chris? Probably 20, at least 20 trips a year. I'm flying. Yeah. I think I could do tours through IAH, the airport in Houston now. You know the one rule that I've never understood. I mean, it sounds like it's in theory is you have to have your phones in airplane mode during takeoff and landing. Do you know why that is? Somebody out there is going to.
I'm sure somebody has.
Look,
read.
Miss Producer is shaking her head. You want to fill us in, Miss Producer? Go ahead. Come on. Why?
You can't hear me.
I know, but I can relay what they're saying. Come on. This is your moment to be on the show.
I've heard.
Heard is key word.
That the data signal gets stronger because it's trying to find an antenna.
Oh.
The farther away you are, the stronger it goes, and then the more interference it has.
Oh, so just so the audience caught the myth of why this exists, it's because as the plane takes off and you get further from the tower signal gets stronger, which interferes with the aimplane.
I think it's psychological. It's just getting everybody prepared to say we're about to take off, pay attention to the flight attendant, and hear the safety instructions.
Mike, you want to take a stab at why they make you put your plane in airplane mode during takeoff and landing? Do you have a thought on this?
Because they can.
Wow. I think the audience got a glimpse of the mic. I like that.
That's called a flex.
So I will say, Miss Producer, I think categorically reject your answer. I don't buy that at all. I've heard something else, which was, interference, but not related to that. But I think they disproved all of that. Anyway, my whole point is nobody knows where this rule came from. And that's a lot like today's topic.
We haven't talked to the right people. That's what this podcast series is for, is the untold stories
of why we
do things, bro. This is why we bring people on the show like Mike and all the other great people that we've had on.
So just before we get into this, and we're going to introduce our guests in a moment.
So we're not going to make something up is what you just said?
I think we already, about why the regulations are.
We just make something up.
You can, because you know what we're going to talk about. So audience, I'm going to ask you to think about the dent regulations we currently have. What have you heard about where 6% deep comes from? What have you heard about where the original strain limits in B31.8 came from? You've probably heard a bit of myth and a bit of fact. Today, we're going to be talking to our esteemed guest. That's the word I've learned you have to use. You want to make people feel good about themselves, you say esteemed.
Esteemed.
Our esteemed guest, Mike Rosenfeld. So, Mike, I think you've introduced yourself before on the podcast. You're a return guest, but you got any words you want to introduce yourself to the audience before we jump right into this topic?
Sure. Mike Rosenfeld, Chief Engineer with RSI Pipeline Solutions, RSI.
It's right there. I saw you came Brandon on the show. I liked it. It's a nice shirt, by the way.
It is. I favor white. I don't know if you've noticed. I really like white shirts. I like your shirt. I like the color.
At the last minute, I decided to put this shirt on. Before that, I was wearing a white T-shirt with the Surf Ohio logo on it. So Surf Ohio is a colossal joke because of.
I was gonna say
Ohio's
I have a feeling like
I was
Ohio
wondering, I was
versus
like-
Michigan. I was like, this has to be a rivalry joke.
No, surfing.
Yeah, I know.
Ohio's a landlocked state.
That's why I said this has to be a rivalry joke.
No, it's just a joke.
Yeah. It'd be
Although
good to see if anybody in the audience caught it.
Ohio does have the North Coast.
Can you surf on? Wait, what?
No,
Y'all,
you can't.
I was like, wait, hold on. Do the waves actually get big enough there? I had to pause and think for a moment. I was like, am I making a stupid comment?
Actually, they can get some pretty big waves during a storm, like in the winter or something. I don't think you'd want to be there.
So, all right. Well, Mike, today you're on to help us sort through the history of dent-based criteria in the United States. Hoping to set the record straight. I know some of this. Some of it, though, you shed some good light on in our pre-meetings. And so what I'd like you to do, if you don't mind, is for our audience that is out there, you guys are familiar with it. There is a depth-based limit of 6% that's been around for a long time. And then 2% on seam welds. Can you shed some light, Mike, on your opinion? Where does that come from? How did we get there into that portion, those criteria in the code?
Yeah. So the depth-based criteria do have a long history in the ASME pipeline standards, B31.8 for natural gas, and a different history arc for B31.4 for hazardous liquids. If we go back to the first B31.8 standard in 1955, the depth criterion was for new construction, 1/4 of an inch in pipe operating at 50% of SMYS or more. And that's a pretty tight criterion. So in 1963, that was revised to 1/4 inch or 2% of the pipe diameter in pipe larger than a 12-inch nominal pipe size and pipe operating at stress levels of 40% of SMYS. But there were no maintenance specific criteria at that time.
So wait, let me make sure I understand that correct. Hold on. So 1956, this is well before OPS. This is well before 1955, well before what we call, what do you call it?
IMP 1.0.
IMP 1.0, right? So I'm going to say something ignorant. I think a lot of people think 6% came about in the code, but it was clearly predated in B31.8, 1956. And you said something that I had to stop, because in my mind, I was already wondering, which is, you said there was no maintenance portion. So this was just the design portion of the code?
Well, the construction portion.
Portion.
So you were supposed to visually examine the condition of the pipe and the condition of the coating, examine the condition of the pipe before you coat it, because a lot of coating was done in the field. Then
True.
examine the condition of the coating and the pipe before you lower it into the ditch and bury it. So it was a construction standard. And also you would want to find this damage before the construction contractor folds his tents and disappears. So in 63, it became 2% of the pipe diameter in 12-inch in pipe larger than 12-inch nominal. And the same criterion was introduced in B31.4 in 1971. Their first editions didn't talk about that. So that was introduced in 71 for hazardous liquid pipelines.
So B31.4 had no construction-related dent depth criteria until 1971 when they took it from
Correct.
B31.8. Well, we say they took it. Maybe they did it on their own.
No, I
Mirrored
think
it.
who knows? They came up with exactly the same criterion, although their limit was pipe operating at hoop stress of 20% SMYS instead of 40.
Okay.
So, and then for the gas code, for maintenance purposes, the code stated that injurious gouges, grooves, and dents would have to be removed if you discover them, but they didn't define what was injurious. And that persisted through the 1992 standard. But then in 1995, the code said smooth dents do not require repair unless they contain stress concentrators or affect girth or seam welds, which makes them not smooth dents, or the depth exceeds 6% of the diameter. So that was in 1995.
Wow.
And so my recollection, because I had just started getting involved with B31.8, maybe around 91 or 92. I distinctly recall a discussion at a committee meeting. So this, if it came out in the 95 code, this might have been around 93 or 94, about doing a survey of inline inspection vendors at that time to determine what size dent their tools could travel past without basically coming out in pieces, such that you couldn't get a reliable assessment downstream.
So these are caliper and MFL tools like we think of today. This is like the age of tuboscope.
Yeah. I mean, there was back in that day, there were some of the same players. There was Enduro, there was TDW with their caliper tool. There was Tuboscope and Vetco. At one time, they were separate companies, but then they merged, and I'm not quite sure when that occurred. And I believe that, and PII was also in the mix then, and another company called Nausco, which became BJ Services, and Nausco, actually, they had an interesting deformation tool that used sonar to ping the inside wall and get an echo for essentially geolocation of the deformation. So, and then on the liquid side, there was also Pipetronics, which I think was UT based. So, but some of those companies aren't around anymore. They've gotten
bought, merged, absorbed. Yeah.
Different ILI companies. And I think it was an informal survey because, look, there may be half a dozen companies to call up. So somebody knew somebody and talked to them, and the got a variety of answers. And the lowest or most limiting case was a dent 6% of the pipe diameter. That's what went into the code.
It makes us think, Mike, that that was like a constraint for the pig, right? So that the pig could traverse. So then that makes me think that the logic was then the pig described it. Well, if the pig can describe it, then at what point do you say it needs a repair? So I get the logic for saying this is an issue, but that seems more for pigability, not necessarily for integrity.
Yes, that's correct. It's a pigability issue. There was testing that had already been done many, many years earlier. I think the first kind of well thought out set of tests was done by a pair of engineers, Bolanos and Ryan. They were working for Columbia Gas Services in Columbus, Ohio, and they performed pressure testing on samples of pipe that they, introduced dents of specific proportions and depths, and some were smooth and some had gouges in them, and put end caps and pressured them up. And so what they found was that really deep dents, the pressure would just push the dent out round. And as long as it didn't have a scrape or a gouge in it, it didn't really affect the burst pressure of the pipe. So, then that was in 1958, 59, sometime like that. And that was published in an oil and gas journal article. Then in 1960, Bob Iber and George McClure, who were involved in a lot of fracture control studies that came maybe a few years later. So they were at Battelle. They did a study for the American Gas Association, the Pipeline Research Council, which was, those two were tied together at that time, where they did a lot more testing, looked at a lot of a broader range of variables. And what they found was that dents as deep as 9 or 10% of the pipe diameter didn't, as long as they were plain dents, did not affect the burst pressure of the pipe.
Yep.
So that 6% criterion is not a direct integrity related parameter. It's, as you said, Chris, it's for piggability.
So I wonder, Mike, so this is around the time when Kiefner and Fowler from Struss were doing some of the early testing work too. And that went into 1156, if I recall. That was the API standard on rocks dents that like appeared and then was retracted. Do you know the depth limits of that test? Because for some reason in my mind, I have 6% as the depth limit from that test too that I thought they worked in. So I'm wondering if the 6% limit, which then appeared in 1995 and is around the time that Kiefner and Fowler are doing their test at Struss, if it worked its way and then limited their test to 6% incidentally too.
Perhaps. I don't recall that. And I'm not sure which came first, now that you mention it. Whether, I don't recall the publication date of the 1156, but it might have been around then.
Yeah.
And they were, to be honest, I think they were more concerned with the process of, or dents with scrapes or gouges, and validating the process of buffing those out to a smooth contour.
Yeah.
So there was an equation in the Canadian standard at that time that was a sort of a conservative version of the original B31G equation, but nobody really knew where that came from. And so API funded a study carried out by Stress Engineering and Kiefner and Associates to at least try and validate that, which they did. So they showed that that you could remove the mechanical damage by buffing it out within limits. And they defined that, hey, look, if the damage is really bad, like if you have to remove more than 40% of the wall, that can't be your only repair, because there's evidently invisible damage that just buffing it out doesn't take care of. But that's a different issue.
So what I'm wondering still, though, is, like one of the ongoing debates in 1183, not ongoing, but one of the things we run into is that currently, if you have a dent with metal loss, we assess the burst pressure from the metal loss using B31G, right? Which is consistent with that. You keep referencing the B31.8 injurious dent portion. And it basically says that for dents up to 6% deep, go ahead and assess the metal loss according to B31G, and then assess the dent to the other criteria.
Yep.
And that has effectively established a limit of 6% for dents with metal loss, because we have no code guidance that says if it's 7% with metal loss, you can still assess the corrosion using B31G. And it put a hard limit in 1183, and it's worked its way even still today into some of the dent ECA procedures. Like if we have a dent with metal loss and it's a 7% deep dent with metal loss, are like, well, we have no test data, no code data to support analyzing greater than 6%.
Well, actually, it's funny you mentioned that. In the early or mid 90s, say sometime between 1990 and 1994, the EPRG had a recommendation of 7%.
Did it?
Yeah.
Now I'm gonna have to go look. Now you made me go look. So I feel like I'm gonna actually have to follow up with these questions in the audience. I feel like I'm gonna need to ask Kiefner when we talk to him. Say, hey, did y'all test greater than 6%? Get the answer to that on that 1156. And then I'm gonna have to go look and see if EPRG had a recommendation of 6%. See if somebody else out there had a recommendation for greater than 6%.
Okay, so, but here's the other thing related to something that you mentioned, which is corrosion in a dent. And B31.8 allows you to evaluate corrosion in an otherwise plain dent, the same as that exact same corrosion in an undented pipe.
Correct.
And so does the current edition of ASME B31G, which got totally rewritten in 2009 and has been successfully updated every couple of years since. And so, and that was based on those same tests that were carried out by Stress Engineering and Kiefner and Associates, where they looked at just plain metal loss, not where the metal loss is removing a gouge. Okay, so there does seem to be a difference between metal loss due to corrosion versus metal loss where you're trying to buff out true mechanical damage that has, that traumatized microstructure at the gouge and that could have a crack and stuff like that.
Yeah.
Yeah, that's where those come from.
One last thought. We spent a lot of time talking about dents with metal loss, right? But the seam weld portion is still 2%.
It
is the
is.
seam weld portion with 2% just purely carryover from the 1963 definition for construction, and it's just never been updated?
No, I do also recall a discussion at B31.8 about the problem with indentations affecting seams and girth welds. And seams and girth welds don't necessarily have the same tolerance for strain as smooth metal. And so I think at least for the for the construction portion, the feeling was that, of course, the construction part for the gas code didn't change. It's still 2%.
Yeah.
Period. For operations and maintenance, you can invoke instead a strain criterion, which we haven't talked about yet.
Mm-hmm.
It's not as liberal as for plain pipe, but you can go to a higher strain. But it still recognizes that girth welds don't have the same kind of strain capacity. But
somewhat arbitrary in terms of the limit that was put on it. I guess
that
was my thought.
It could be, and of course, the B31.8 code allows a pipeline operator for maintenance purposes, to come up with their own criteria for whatever they're doing based on an engineering analysis.
the catch-all. I forget what it is. We've debated that before. There is that catch-all phrase. So, okay, this is a good point. We're going to pause. So, audience, you heard it. 6%. I think many of us expected that it was a tool passage issue. Mike confirms it is indeed a tool passage issue, but dating way back and borrowed even from earlier versions. So we come back, we're going to talk about maybe a little more of a fun topic, one that's near and dear to my heart, which is, where does 6% strain come from? First guess from Chris was 6% deep, 6% strain. Why not? You'll find out when we come back. All right. Welcome back, audience, as we continue our conversation on the hidden truth for dents and pipelines with our guest, Mike Rosenfeld. So, Mike, you closed us out at the end of the last section with the origins for the 6% deep criteria in B31.8. And you mentioned that, again, it was the depth origins come out of the construction portion of the code all the way until 1995, which is when 6% gets introduced. And per your recollection, seems to be based on an obscure survey of ILI vendors and depth-based. But that's not all the story, right? There's something else that you didn't share with the audience?
Yeah, there's a little bit of a plot twist, which is that in 1986, which is 9 years earlier, the B31.4 standard changed their dent depth acceptability criterion from 2% of the diameter in 12-inch or larger pipe to 6% of the diameter in pipe larger than 4-inch nominal pipe size. And so this was, as I said, 9 years earlier. And I have tried to investigate this with, people who currently are or formerly were involved with B31.4, going back into the 90s, or in one case, who was a member of the committee at that time. And none of them have been able to state what the basis for that change was. Now, maybe they did, maybe the B31.4 committee did their own survey of ILI companies and they were concerned about piggability, and maybe B31.8 actually picked up on that from them. I don't know, but they may also have been tired of I don't know, cutting out dents that were only 2% of the pipe diameter.
That's what I'm arguing. That somebody got some construction influence on the code at that time.
That's what I'm thinking too.
So
consensus came from consensus. We need to stop fixing
I will say
these.
this much: the ASME committee, at least today, Mike will probably defend me on this. I feel like the ASME committee is pretty guarded in their ability. They don't make rapid changes, and they don't succumb to external pressure too often, in my opinion. But that's just my opinion of the 31.4 and 31.8 committees.
Well,
All right,
you're right. We're on the code committees. We're kind of lazy and don't really want to make changes. So,
Is it lazy? Is it lazy, or is it more
it's a combination? Yeah, it's a combination of if it's not broke, don't fix it, or
That's
being
true.
conservative, and also things exactly like this where we don't know why it says what it says. So you got to be careful about making changes, because
So do we just need another big dent empirical testing program? That's
Oh,
what this
Lord,
seems like.
yeah,
I think we just need another
that's
one.
great.
Maybe
Don't-
somebody
don't
there
go there.
says we need to do a JIP and just test a whole bunch of this stuff.
Don't go there.
And then we can debate between 6 or 7, right?
So
6, 7.
I went ahead and asked. I went ahead and asked Gemini, and Gemini blames it on a buffer. That what Mike said is that dents less than 10% don't affect a burst pressure of a pipe, so they just applied a safety factor.
You do
and
know,
put
like
6%.
nobody in the audience knows what you mean by Gemini, because we all use Copilot and ChatGPT.
I'm sorry,
So why would you
Gemini,
do that?
it's-
Like nobody uses Gemini.
But you know what? So Gemini's Samsung's version, but you know what nobody talks about? Apple's version. So
you're right.
thank you very much. All right, Mike, this is the more fun conversation for me. The origins of strain and the limits in B31.
Let me guess.
Right?
The limit is 6%.
Yes, it is.
Of course it is. Why not?
Why
Yeah.
6?
It was.
Why not? Why not?
The mark of the beast, 666. That's what this is.
Because they're so bad for you. Dents are just so bad.
Oh my gosh, that might be the first religious reference on the podcast. That's so funny. So,
That's
no,
funny.
so that our audience is familiar, the 6% limit. If y'all, so going back to the first editions of B31.8, and everybody knows this, pre-2018, the code allowed you to evaluate dents with strain, and starting in 2003, and the limit was originally 6%.
Right.
Voila.
Yeah. Well, I mean, first of all, I think the question is, why are we even looking at strain?
That's fair. All right, take us back.
Okay. Right. So, and who was doing it? And there were a lot of people involved with that. And I believe that first of all, why strain? Well, because a ductile material, and most line pipe actually is ductile. Even older line pipe materials
True.
are ductile, and a ductile material hails from TMS, too much strain. And-
Didn't we? Hold on.
Oh
When
my
you
gosh.
came on for PPIM, didn't you have your own acronym back then too? You had a hardness
Hussey.
in
The Hussey index.
That's right.
I forget. He's trying to get away from it. Let's keep.
Now he has a TMS. I love this. Too much strain.
So, well, prove me wrong. So in around 1994, Dave Warman, who he works at Crest now,
Yeah.
but
Yeah.
he was working at Iroquois Pipeline, Iroquois Gas Transmission System, rather. And the Iroquois line was faced with some kind of big dents
Challenges.
left over as a result of construction. The contractor didn't do a super job of preparing the ditch bottom. There were also some big rocks in the backfill, and they tested to a high stress level. So when you have the weight, when you've got a pipe sitting on a rock, and then you add the weight of a meter of dirt over it, and then you add the weight of water in the pipeline, and then you take it up to a hoop stress of 100% SMYS or higher, you're going to have areas where around the contact there where you exceed the biaxial yield strength of the material during the test, and the pipe is going to wrap itself around that rock. So you end up with big honking dents. And so they had some of these things. And so Dave and another guy named Jim Justice, who was a Trans-Canada engineer. Iroquois was actually a Trans-Canada project. They were at that point starting to think about strain as an alternative for accepting dents rather than the depth alone. And what their criterion was a strain of 3%. And what they would do is they developed a process in the field for examining dents using like a contour gauge to and then tracing that profile onto a piece of paper, or just comparing it against say a
Printouts.
curvature, pre-drawn curvature that could indicate what the strain level was. Because if you take a straight piece of pipe, a straight plate, and you bend it to a curvature, you're introducing strain. All right, so there's a relationship between the curvature and the strain. And their strain criterion was 3, and that was based on an attempt to be conservative against a strain limit of 10%. Where does 10% come from? Well, when you're doing qualifying a welding procedure or a welder, you do the root bend and face bend test. And for typical ranges of pipeline wall thickness, that's a strain, that bend test is a strain of around 10%.
I did not know this.
So they wanted to go to 3% of that. And what they were doing too is they were only measuring strain either in a longitudinal axis or a transverse axis. They weren't trying to combine them or anything like that. And the strain was purely based on change in curvature. And I got involved with that for a couple of reasons. One was that I was able to provide Dave with an ASME code-based justification for that 3%. And because they wanted that for to try and persuade the DOT that these dents were going to be okay. And the relationship was that nowhere in the code at that time was strain levels up to 3% prohibited, and or even higher for that matter. Didn't talk about it. And when you look at cold field bends, the allowed bending radius for pipe came to strain levels, typically between 2 and up to 3%. And nobody gets it, all bent out of shape about straining
Cold
your
bending.
pipe up to 3%. So if it's okay for a cold field bend, why can't it be okay for an indentation? And so that was the reasoning there. Then the other reason I was involved too was that the presence of these dents and the rocks, in the ditch and stuff like that, led into some contentions that the pipeline was not constructed in accordance with its, FERC construction permit, and so there was a lot of other. There was a big sideshow associated with that. So,
So at this
that,
time, this originates because they need an alternative criteria other than depth for a pipeline that has a lot of dents. And what they
Yep.
resort to in the field is uniaxial, one axis or the other, comparisons of curvature using a contour gauge. You know, it's fun. I actually got one of these in my email box, I swear, yesterday. I have not seen a legitimate one. And I got a dent field report with a carpenter's contour gauge.
yep,
And they were comparing the curvature to printouts on a page. And I was like, oh my God.
Yep.
I've talked about this, but never actually seen it.
yeah.
Right.
So,
In all fairness, it was, I gotta be honest with you, it was somewhat effective.
Mhm.
Better than some calculations that I've seen from optical scans, I will say. But
Yeah.
anyway, so this goes, and y'all need a basis. Y'all's first rational starting point for a basis is 3%, which you rationalize as being, we've been bending pipe this way empirically forever with no problems. All right. So we're at 3%. How did you get above 3? Well, I know
Well-
why you got above 3 because they asked you to, but how did you get above 3?
well, right. So, a next step in that process was that I was approached by Rich McGregor, who I knew he was a former Iroquois engineer. I knew him during the time of that Dents work at Iroquois. He was now at Great Lakes Gas Transmission, also a TransCanada asset. And he had a situation involving two big dents in the bottom of one of their pipelines, where the dents were quite deep, like 9 or 10% of the pipe diameter. The dilemma for them was that they were out in the middle of a river, and it was
Of
going to
course.
cost a couple of $1 million to go remediate that. And he asked a perfectly reasonable question: do we really need to repair them? And so that's where you start getting a little more serious about trying to evaluate the strain in a dent. And so Dave and I had both together and separately been going around measuring, using a contour gauge to measure strain in one axis or another. But then this brought up the question of doing that using what you can get out of a high resolution geometry or caliper type tool. And so they were using a high resolution caliper tool to do that. And so it was using that data and some manual processing of that data, it was possible to show that even though these dents were quite deep diameter wise, the actual strain levels were pretty low, because the strain levels were maybe 2 or 3%, just because they were spread out over such a large area on the pipe. And so I think this really gave some permission to contemplate large dents on a strain basis. And the other thing too is that some pipeline operators, gas and liquids, have encountered situations where the pipe is sitting actually on a very sharp, pointy rock.
Mm-hmm.
And so the acute contact can lead to a very sharp indentation with a crack. Okay,
Yes.
and it leads to a punching or shear crack that leaks, and yet the dent depth is within, say, the 2% acceptance limit. So what that showed was that dent depth and dent strain are not
Correlated.
at all related.
Not good metrics.
Yeah, and also right at about that time, so that was probably in 96 or 97, and probably in between the stuff that Dave and Jim Justice were doing at Iroquois and that, I had been approached by Jim Cox, who is a metallurgist with Plantation Pipeline. That's a hazardous liquids pipeline. And Pat Porter, who was with Tuboscope Vetco at the time, to come up with an algorithmic approach to using ILI data to calculate strains. So, these things were all sort of converging
Coming
at
together.
about
Yeah.
the same time.
Around 97, you said?
yeah, which is actually 2 years after the B318 code had introduced the strain limit. So, so these things were all kind of happening at about the same time, and I think I don't remember who introduced the issue or the question at B31.8. It might have been me, but maybe not.
Go ahead and take credit for it.
Yeah, well, I don't want to take credit if I didn't do it. I just don't recall. And but that led to the 6% strain limit. Now, where did the 6% strain limit come from? That 6% is a pure coincidence compared with a depth of 6%, because those two things don't relate to each other. But the 6% did come from me, because I had done a survey looking at
Another informal survey or a formal survey this time?
Or you heard something from somebody
it was
once.
It was an informal survey for an operator, not a Trans-Canada pipeline system.
Yeah.
Of dents on their system. Actually, I think it was the Algonquin system. And looking at, well, that and some other dents related information, for example, from Colonial and a few others. And so I looked at dent depths, and I calculated dent strains in, sort of a biaxial strain, looking at the changes in curvature in both the longitudinal and transverse axis, and also the amount of stretching in the pipe that you get with a dent, and looking at those strain levels. And the lowest apparent amount of strain where there was a crack was 12%. So, a typical ASME codes approach was, well, the worst that we saw was 12%. So we'll just put a factor of safety of 2 on that and make it 6%.
And voila.
So that's where the 6% strain comes from.
And you were looking at what data when you came up with the 12%?
You both asking how many statistical
No,
relevance?
we're getting there, bud.
Like a dozen and a half dents or something, where
A dozen and a half dents.
yeah.
Is the half a dent that pushed it over the edge?
The other question is what was the data from? Where'd you get the data from? Was that, you said that was ILI data or that was field data?
No, these were field data or cutouts.
Okay.
So, and that's another source of randomness in that sort of analysis, which is that the dents that you measure in the field or the dent that you measure in a cutout is not the same as the dent that you measure, with inline inspection. But nevertheless, what we had were
So I want to get it
cutout
straight.
pipe.
So the 6% strain limit came from about a dozen dents that you looked at.
About a dozen and a half.
Not a half
But-
dent, but maybe
No,
about 18.
no, that's not 12.5. That's 18.
Oh, I was wondering the same thing. I was like, it was a half dent. What's a half dent? Now it makes sense.
In the
So
failure
give or
analysis, they
take.
cut right down the middle of the dent, so he just had half of the dent.
It's half dent cut out for the field. I was so thank you for clarifying that. So that's really funny. So there
Is that
it
enough
is.
dents, Rhett? I mean,
You know,
didn't 1183 look at like a couple thousand
Look,
dents, maybe
but
like
let-
30,000
look,
dents?
Mike, since you were there, and I've got the strain criteria has been great in terms of transforming gas integrity management for dents, and it's persisted now for well over 23 years, and it's been refined and made improvements and all that. But I wonder if you now could go talk to you in 2000 when you were probably projecting that for the code and said, Mike, do you know how set in stone this 6% is going to become? Because 6% still persists today. CSA still 6%.
Yeah.
Like,
Well, no, I suppose that wasn't obvious to me at the
it
time.
never is, though, is it? When we put this stuff into codes, that's
Yeah.
the truth. I mean, working on code committees, we do the best we can.
Yeah.
And the funny thing is, we put things in there, and it's just what makes me realize is how difficult things become to change. I mean, I joke about this. Figure 4 is probably one of my favorite sacred ones ever. Like,
Yeah.
there's so many
Yeah.
things in the code. And so 12% was based off of give or take 18 dents and lowest observed level of cracking. I have
With a
heard that
factor of
before.
safety of 2.
With a factor of safety of 2. Not 1.4, not 1.37, 1.39. None of our other standard safety factors, just 2. Got it.
Yeah.
That's great. Well, how about welds? Where'd you get welds from then? Because you put welds at 4%.
Right. And and you know what? That was also a typical ASME codes-based decision. And I remember sitting around a conference table talking about what should the number be, and we were debating it should be this, that. But basically, I went around the table and said, "What number would you be comfortable with for a weld?" And the
Oh, good Lord.
result of that was 4%.
I'm just wondering if you did that today. I feel like people, 20, 22, 30? Can we get 30?
That would probably get shot down because we know that's really not gonna work. Could it
But
have been
it's whoever's-
5%? Could it have been?
Whoever's bias comes to the table is what I'm getting at. That's the fun part. So,
Yep. Now,
so that's so much fun.
B318 did in 2018. They did
Update the
significantly
calculations,
raise
yeah.
those strain limits because a lot of pipeline operators were kind of squawking about.
Yeah, they
6%
fixed the
being
equation
too
to some other things. I mean, I never thought that the error in the equation was that aggressive. But one of the limits is we never actually we have yet to touch the weld limits portion of that, right? And you and I have even chatted about that actually probably needs to be updated, but we really don't have good data for it. It's the truth. And I don't know if we're willing to sit around the table and ask that same. That would be fun. You know what? I might do that. My next 31.8 O&M committee meeting. Just say, guys, I want to change 4%. Around the table, what are we all comfortable with?
Just yay or nay. Just anybody willing to do this. That's the first step.
I should totally do that. Oh, I know Evan's chair. He's probably, if he listens right now, he's probably rolling over. So, my goodness. Well, Mike, hey, this has been fun. I hope, if you think of some other good stories that the pipeline industry needs to preserve, hopefully we've laid to rest some of the myths around dents. So now we know where 6% comes from twice. 6.
It came from about 12% strain, half from about 12.5 dents. So there's just common theme of numbers here.
It is. The next limit must be a multiple of 6. That's what I'm thinking.
We
Whatever
also
we're
like
gonna do.
even numbers is what it seems like. We don't like those odd numbers.
Yeah.
It just feels odd.
12.5 dents. So, but Mike, no, seriously, it's been a lot of fun. To our audience, thanks for joining us. We're going to continue talking to this series. And if you have some other, you know what, audience, throw it out there. If you have some other good questions, you want to know where the heck does this come from in the pipeline industry, send your questions to us and we're going to see if we can get the right people to answer it. But until you hear back from us again, we're going to sign off on this episode of Pipeline Things. We'll see you back in a couple of weeks. This episode of Pipeline Things, executively produced by Miss Sarah Etier. Thank you very much to our guests from RSI Pipeline Solutions, Mike Rosenfeld and FORME Marketing for allowing us to film at their venue. And of course, my life partner and co-host, Mr. Christopher De Leon.